It has to do with essentially when you try to change a magnetic field, you're going to get an electric field that pushes back. So it's essentially a coil. We'll talk about that, and to well accustomed to inductors. But yeah, so that's the basic idea. If you try to change the current going through an inductor, it's going to fight to keep it the same. So if there's 1 amp going through it, and you change the conditions of the circuit such that either less or more want to go through, it'll stop that, or at least as much as it can. And it'll eventually lose, but that's its behavior. So we have that, for this particular guy, we have something that looks like A sine omega t is equal to, and the other thing, the last thing, how is Q related to I? You guys have seen this already, hopefully. How are they related? No? You guys remember that?
Sorry,
Okay.
QT is that.
Alright, this is A-T related stuff. So this is the situation we have. So if we're going to write everything in terms of Q, we can do that. So we could say that L is, or the voltage across the inductor is actually this. Plus so now we'll start with something that we're used to dealing with. And what we're trying to figure out is what is the charge going
Is
to
that
be?
Q over L for the last piece, or Q over C?
C, sorry. And so the idea is that now we want to figure out what I is going to look like. So we want to find the solution here, but we want to find so what does the homogeneous part of the solution look like?
LQ squared plus RQ plus OC.
Just like R.
So it's the solution to this guy, right?
Yeah.
So what are the roots to this? We didn't be able to do this nicely, so let's just plug this into
Minus.
so you have
Minus R.
so this is the general form here. So if we so we know that all these quantities here are positive.
Well, why do we know that?
Because they're actually fundamental, like a resistance is going to be a positive value. And inductance, so these are all physical quantities that are associated with independent devices. They can't,
So
if
R
there's
is
zero
always greater
devices
than
that they're, sorry?
So R is smaller is always greater than 0?
Yes.
Okay.
Or, yeah. If the device is there and it has a resistance, then it's greater than 0.
Okay.
I guess technically these things can be 0, and that would be the equivalent of the device just not being there. Is there another question? All right. So we have this as these are the roots here. Any other? Yeah. So what do we know so what do we know about this quantity here? If you assume that this quantity here is, we want this to be a real quantity.
So we want that to be.
R squared greater than 4L minus over C.
Alright. So if we're looking here, what do we know about the nature of both of the roots?
Both are greater for, both are positive. Like,
Alright, so if L and C are both positive, right? Then we know that this quantity here, how is it related to R?
it's greater than R. Or,
Has to be less than R, right? So the only way it can be greater than R is if we're taking R squared, adding something to it, and then taking the square root. So we can get above R that way, right? We're actually subtracting here, right? So we know that this is going to be less than R. So we know that the positive root is going to be negative, and the negative root, of course, is going to be negative as well, right? So we know that both of the roots to this guy here are negative values, right? So what does that mean about the complementary solution here? It's going to be of the form C1 e to the R1t plus C2 times e to the 2t. And what do we know about R1 and R2?
Positive.
Sorry?
They're positive.
no, they're negative.
Negative.
No, because then they'll be positive. You put a negative sign in front of them.
Oh, sorry, yes. Yes, that's the roots. My apologies. R1 and R2 are negative. I don't know why I put that. So, then, so what do we know about the behaviors of these roots as time goes on?
So, the other way.
So if R1 is negative and R2 is negative, what do we know about the...
What did you say, so the other approaches zero as time goes on?
There's decay.
It's gonna be monotonically
So-
decay.
The approach is C1 plus C2.
So what do we call these types of solutions?
Transient.
They're transients, right?
But how did we say that they're both negative?
Because this quantity here is going to be less than R.
Oh, yeah, okay.
And so the positive root is going to be negative and the negative root is going to be negative. So if we're looking at this, then for most circuitry, the transients are going to act pretty quickly, and even if they don't, what we really care about is the non-transient part. Right? So for the most part, when we're analyzing AC circuits, we're going to ignore this part of the solution. Right? We're going to deal with a particular part in general. And so what is our particular, how do we figure out our particular part here?
Do it.
Wait, why did we disregard the transient part again?
Because it's not, for when we have kind of circuits fluctuating back and forth, the transient part isn't really going to affect the behavior. We really care about the kind of steady state. The steady state part here is going to be a sine wave. We care about the steady state of the sine wave in each of our independent, or each of our individual components.
But then how do we know to just not use those?
Because they're transient. So I mean, if you're doing circuits in general, then for those types of problems, you'll ignore the transients. You'll be asked for the sinusoidal parts of the solution explicitly. And if you're not asked explicitly, you can safely assume for circuits that we're looking for. We're not worried about the transient part. Sorry, I lost track. Okay, so now we're looking for the particular part. What method should we go about using to find a particular solution?
Undetermined coefficient.
All right, so undetermined coefficient is probably the easiest. We know this is going to look something of the form A. Actually, this guy, let's guess it looks like this. So let's guess that it has this form.
Why do you write it as dash?
So it gets us to our answer more easily. So this is actually the same thing as, so you know there's the sum of angles formula, right? So you can write this as a combination of sines and cosines.
But
Right.
where does the 5 come from?
So this is a guess of the solution. Like we guess the solution is A sine omega t plus B sine omega t.
Okay.
An equivalent guess is this guy here.
Okay.
There, and you can go from one form to the other pretty easy. We've done that in class,
Uh-huh.
right?
Still
Yeah.
no, just the A in the front.
Wait, can we try doing it with the exponential response?
Sure. All right. So if you want to do exponential response, you can do that.
So yesterday, he spent like half the period showing us how scary some problems can get if we don't use exponential response.
Well, actually, yeah, when can you use exponential response? When can you not use? I don't know. You can use exponential response. So when can you not use exponential response?
What is a polynomial?
When it's a polynomial.
Yeah.
There are other instances where we can't use exponential response.
Whenever there's
When the
an
right-hand side
E or a
cannot be
sign
in
or
terms of
Sorry.
No,
Well, you can't be
can use it
reading
when
the
there's a constant.
exponential.
Yeah.
You can't use it when there's an exponential.
So we can't use exponential response if the frequency of. Pretty sure. Actually, I'll hold up on this. I'm pretty sure. So you can use.
Yeah.
No, you can't use it when the frequency of the complementary solution is the same as the frequency of the x. Actually, no. I'll hold off.
No, but then we like just like adjust it by multiplying it by.
Right.
Yeah.
Okay. All right. All right. So let's use exponential response here. So
Wait, leave that. Oh, in this case now.
that there. So what is the form here? So we have this guy here. So what is the form here?
It's gonna be
Next particular is
a
the imaginary approach.
e to the I omega t.
And we're going to be keeping which part?
The imaginary.
The imaginary part. All right. So this is equal to
Divided by p by omega.
So we're going to get that our, I'm not writing x there, our q particular is going to equal to what?
No, I need to divide by p and then omega.
P? No, so this is the, so if you go, you want to find q.
You're finding the Q.
Oh, okay. Okay, gotcha.
So that's going to be, in this case, A over this evaluated I omega, which is going to be what?
Minus
Negative
omega
omega
L.
squared plus omega I.
Plus r plus r.
Well. And so now we want to take the magnitude here. It's going to be Wait, so which way are you guys suggesting? Do you want to turn this into a complex exponential, or do you want to turn this into, use Euler's equation to take this and turn this into just a plain complex number, multiply the two? Plain complex number? All right. So this is going to be kind of messy.
This one would be pretty nasty.
This one is
No,
blocking.
yes, no, kind of. I mean,
Because you're gonna
is it any worse
cosine
than
a
doing it
sine,
right?
and then you'll
Oh,
have
never
the
mind.
bottom of the polynomial, and then you're gonna have to try to isolate the I and the constants, and then take the I term.
it's not going to be that bad. It's, I mean, it's
No, that's all you
the,
have to do for the bottom one is just take the magnitude of it and then find phi.
so this is the form of the block.
Yeah. So this is
Um,
it's not terrible.
So we're going to multiply by the complex conjugate. And we're going to get a over 7 squared. T, then how can you write e to the I omega t?
Sine or cosine omega or I omega. Wait,
Do 6, right?
6 cosine of
Cosine omega
I
t
omega.
plus
Out with the
I
boy.
sine omega t.
And which parts are we looking for?
the
The imaginary.
Imaginary. So that's going to be
Man, how did you get that, Jonathan?
I just remember what we're doing. I haven't really read this. It's not done yet. Times.
This is painful.
That's what I said. Oh no. I must have skipped the wrath of the camera.
Sine omega t. Alright.
Bigger than
Say, you have your laptop open.
So
yeah,
this
but it's
is
a different equation.
So it's an all-around.
the imaginary part.
Paying
So
attention
this
to the
is
map
continuous.
isn't the same as
Um,
paying attention.
But we need to be able to talk about phase
Damn, we're not gonna
lag.
do anymore?
Or we need to talk about phase and lag. So how can we rewrite this
To be less horrible.
to be in the form of a sine omega t minus 5?
Amplitude equals.
It would have been easier to do it the other way.
Yeah, it would have been easier to use coefficients here. But I mean, this is a good practice. This is a good technique to practice. This one gets kind of hairy just because there's so many terms to deal with, and nothing really collapses nicely. But yeah, you get this here. So a useful idea to be able to deal with here, and we'll practice more on this, is with what's called a phasor diagram.
Oh, can you not use that board, Jumbo?
So if you have something that's of the form a sine omega t plus 5, then we can represent it with the vector.
Not everyone can receive
It has magnitude a,
physics overlaps
Slice
with this.
Open
and it's angle phi.
What?
If we want to add together two such guys, if I want to do this,
I forgot. Try to do good things. Try. Just don't
Emphasis on
finish.
try.
two, then you can take any two phasors and add them together like you add together vectors.
Phasor.
And the resultant phasor will be the equivalent of the resultant equation.
Wait, how did you get minus WR cosine omega t? Oh, so it's part of the imaginary part.
Yeah, multiply this times that.
You got this. It's gonna be great.